Something is hiding beneath the surface of Mars. And the deeper scientists look, the less this planet behaves like the dead world we thought it was. It's the kind of discovery that makes them stop, look at each other and say, wait, that shouldn't be there. Today we are going to go deep, literally and figuratively. Because what planetary scientists have been uncovering beneath the Martian crust over the past several years has completely rewritten the conversation about what Mars actually is. Not what it was 4 billion years ago, not what it might become, but what it is right now, today, in this moment, while you are watching this video. And here is the thing that keeps getting buried under flashier headlines. The most significant discoveries about Mars are not happening on the surface. They are happening underneath it. So let us start with what we thought we knew, because that context matters enormously. For decades, the dominant narrative about Mars was one of loss. Mars was the planet that had everything and gave it all away. It once had a thick atmosphere, liquid water on its surface, and possibly the conditions needed for life. Then something went wrong. Its magnetic field collapsed, solar wind stripped the atmosphere, the water either evaporated into space or froze into the polar ice caps, and what remained was a cold, dry, radiation-blasted desert, a geological graveyard, a world that had essentially died. That story is not wrong exactly, but it turns out it is massively incomplete, because while the surface of Mars looks dead, what is happening beneath it tells a very different story. And the more instruments we point at the Martian interior, the more complicated and frankly astonishing that story becomes. Let us talk about water first, because this is where the surprise really begins. In 2018, the MARSIS radar instrument aboard the Mars Express orbiter made a detection that caused immediate excitement within the scientific community. It identified what appeared to be a subglacial lake of liquid water buried roughly 1.5 kilometers beneath the south polar ice cap. This was a genuine shock. The temperatures at that depth on Mars are estimated to be around minus 68 degrees Celsius, which is far too cold for pure water to remain liquid. And yet the radar reflections suggested liquid water was there. The leading explanation for how water could stay liquid at those temperatures involves dissolved salts. Certain perchlorates and chlorides, which are known to exist in Martian soil, can dramatically lower the freezing point of water, allowing it to remain liquid, even in extreme cold. This is called cryogenic brining, and it is the same basic principle behind why we salt roads in winter. But then in 2020, the story became even more remarkable. Researchers analyzing a broader dataset from MARSIS identified not just one, but multiple radar anomalies in the same region, multiple potential liquid water bodies, one large central area surrounded by smaller patches. This was no longer a single anomalous reading. This was beginning to look like a system. Now some scientists pushed back. They argued that the radar reflections could potentially be explained by other geological materials, certain types of volcanic rock or carbon dioxide ice, rather than liquid water. This is how science works, and it is healthy. But the debate itself is fascinating, because even the alternative explanations point towards something extraordinary lurking beneath the Martian South Pole. And this is where we need to pause and let that sink in for a moment. If there is liquid water beneath Mars right now, even cold, briny, barely liquid water, the implications for life are staggering. We know from studying extremophiles on Earth that life can survive in conditions far more hostile than most people realize. There are microorganisms thriving in Antarctic subglacial lakes, in highly acidic environments, in deep ocean hydrothermal vents, in conditions that would kill most living things instantly. The threshold for what biology considers livable is much wider than our comfortable human experience suggests. A subglacial brine reservoir on Mars would not just be liquid water. It would potentially be shielded from surface radiation. It could contain dissolved minerals from surrounding rock. It might have access to chemical energy gradients. In other words, it could be exactly the kind of environment where microbial life might persist, even on a world that looks completely dead from orbit. But the water story is only part of what we have found. In 2019, the InSight lander arrived on Mars and began doing something no mission had ever done before on another planet. It started listening. InSight carried a seismometer called SEIS, the most sensitive seismic instrument ever deployed beyond Earth, and its job was to detect Marsquakes. What it found fundamentally changed our understanding of the Martian interior. First, Mars is seismically active. This might sound like a small thing, but it is actually a significant revelation. Before InSight, we genuinely did not know how much internal geological activity Mars retained. The assumption had been that Mars was largely quiet, a geologically dead world, with only occasional minor tremors. InSight proved that assumption wrong. Mars experiences hundreds of quakes per year, some of them quite significant. But here is where it gets genuinely unexpected. In May 2022, InSight detected the largest Marsquake ever recorded. It registered at a magnitude of approximately 5, which on Earth would be a moderate quake, but on Mars, given the planet's smaller size and different geological structure, this was enormous. The seismic waves from that event traveled through the planet and gave scientists an unprecedented look at the deep interior of Mars. And what they found inside was surprising in ways nobody had fully predicted. The Martian mantle appears to be more heterogeneous than models suggested. There are regions that seem to behave differently from their surroundings, indicating that Mars is not the uniform, cooling rock ball that simpler models assumed. There is evidence suggesting that portions of the Martian mantle may still be warm enough to drive some geological processes. Not the vigorous plate tectonic activity we see on Earth, but some residual thermal energy that has not fully dissipated. This matters because geological activity is one of the key ingredients for habitability. Volcanic regions on Earth provide chemical energy that sustains entire ecosystems in the deep ocean. If Mars has residual geological activity, even subdued activity, then there may be regions in its subsurface where heat and chemistry combine in ways that could support life, or could have supported it far more recently than we ever imagined. The InSight data also revealed something unexpected about the Martian crust. It is thicker than expected in some regions and shows a more complex layered structure than previous models suggested. The top layer appears to be highly fractured and porous, which is actually very interesting from a habitability standpoint because fractured rock can store fluids, create sheltered environments, and support the kind of chemical gradients that microorganisms on Earth routinely exploit. Now let us bring in the methane question, because this is the one that has been driving scientists absolutely mad for years. Methane is a fascinating molecule in the context of Mars. On Earth, the overwhelming majority of atmospheric methane comes from biological sources. Living organisms produce it as a metabolic byproduct. But methane can also be produced geologically, through processes involving water and certain types of rock reacting with each other at high temperatures, a process called serpentinization. On Mars, the Curiosity rover has been detecting methane in Gale Crater on and off since 2012. Not consistently, not in large quantities, but in periodic spikes that have no easy explanation. The detections are particularly puzzling because Mars has no known active volcanoes, and atmospheric methane on Mars should be destroyed by ultraviolet radiation relatively quickly. So if methane is being detected, something must be producing it, repeatedly, from somewhere. The source remains genuinely unknown. That is not scientific hedging. It is the actual state of knowledge. Teams of researchers have proposed biological sources, geological sources, seasonal effects, subsurface reservoirs, even the possibility that Curiosity itself is somehow involved, though that explanation seems unlikely given the careful controls in place. None of these explanations has been definitively confirmed or ruled out. What makes the methane mystery particularly relevant to our broader story about the Martian subsurface is that the leading non-biological explanation, serpentinization, requires liquid water interacting with certain minerals at elevated temperatures. In other words, if the methane is geological in origin, it is pointing us toward exactly the kind of warm, wet subsurface environment we have already been discussing. The different strands of evidence are beginning to point in the same direction. Radar detections suggesting liquid water in the deep subsurface. Seismic data revealing that Mars retains more thermal energy than expected. Periodic methane detections that require an active source somewhere beneath the surface. Each of these findings, taken alone, is interesting. Together they form a picture that is genuinely extraordinary. They suggest that Mars is not a dead planet. It is a planet with a complex, active interior that we are only just beginning to understand. And that interior may contain environments that have been habitable far more recently than the surface has been, possibly right up to the present day. Let us zoom out for a second and think about what this means in the context of Mars exploration history. We have been sending missions to Mars since the 1960s. Generations of scientists have devoted their careers to understanding this planet. We have photographs of nearly every feature on its surface. We know its atmospheric composition in exquisite detail. We have analyzed Martian rocks with instruments sensitive enough to detect individual molecules. And yet the most fundamental question we have about Mars, whether it ever harbored life or whether it still does, remains completely unanswered. That is not a failure of science. That is a testament to how genuinely difficult this question is, and perhaps more importantly, how deep the answer might be buried. Because everything we have learned in the past decade keeps pointing us downward, not to the surface, where rovers drive and cameras capture beautiful panoramas, but kilometers beneath it, where liquid water may pool, where geological heat may linger, where the relentless surface radiation cannot penetrate. The Mars that matters most for the question of life might be a Mars we have never directly touched. This creates an almost philosophical tension in Mars exploration. Our most powerful tools for searching for life, our rovers and landers, are all surface instruments. They are extraordinarily capable machines, but they are essentially limited to the top few centimeters of a planet whose most interesting secrets may be hiding kilometers below. It is a bit like trying to understand the deep ocean by walking along a beach. So what comes next? What does the future of Mars exploration look like given everything we now know or suspect? The scientific community is increasingly focused on subsurface access. Several mission concepts have been proposed for drilling deeper into Mars than any previous mission, creating seismic networks with multiple instruments to better map the interior, and deploying more sophisticated radar systems to continue the search for subsurface water. The challenge is that drilling deep into another planet is extraordinarily difficult and expensive, and the technology to do it remotely and autonomously is still being developed. There is also serious scientific interest in the Martian poles. The South Polar region, where the radar detections of potential liquid water were made, is an extremely challenging environment to operate in, but it may be precisely where we need to go if we want to answer the question of whether Mars currently has liquid water anywhere on its surface or near subsurface. The Mars Sample Return mission, which aims to bring physical pieces of Mars back to Earth for analysis in our most advanced laboratories, is another critical piece of the puzzle, though it has faced significant budget and scheduling challenges. If those samples contain evidence of past biological activity, it would be one of the most significant scientific discoveries in human history. And the samples being collected by the Perseverance rover are being selected specifically from environments that ancient Mars data suggests were once habitable. But here is the thought that I want to leave you with, because I think it is the most profound takeaway from everything we have been discussing. Every time humans have looked at a seemingly hostile environment and assumed nothing could survive there, we have been wrong. Deep sea hydrothermal vents, frozen Antarctic lakes, acidic hot springs, radioactive environments near nuclear disaster sites. Life has surprised us again and again with its tenacity and creativity. The definition of where life can exist has expanded dramatically in just the past few decades of research. Mars, from space, looks like a dead world. Its surface is cold and irradiated and dry. It looks like a place where nothing could survive. But beneath that surface, the evidence is quietly building that Mars may be far more interesting, far more complex, and far more potentially alive than anything on the surface could suggest. The radar says there might be liquid water down there. The seismometers say the interior is warmer and more active than we expected. The rover data says something is producing methane periodically from an unknown source. The geological record says that deep, protected environments could have stayed habitable long after the surface became a desert. None of this proves that Mars has life. I want to be very clear about that, because extraordinary claims require extraordinary evidence, and we are not there yet. What we have is a growing body of evidence suggesting that Mars has, or recently had, environments where life as we know it could potentially exist. That is not the same as finding life, but it is a very different situation from the picture of a simple, dead, cold rock that dominated scientific thinking for most of the 20th century. Mars is not what we thought it was. Its secrets are not written on the surface, where our cameras can see them. They are buried beneath kilometers of rock and ice, in dark, cold, pressurized environments that our instruments have only just begun to probe. And whatever is down there, whether it turns out to be geology or chemistry or something far more extraordinary, it has been lurking beneath the Martian surface for billions of years, waiting for us to find the right tools to even ask the right questions. We are getting closer. Every mission, every dataset, every unexpected anomaly that refuses to fit our comfortable models is a clue. And the fact that Mars keeps surprising us, keeps refusing to be the simple, dead world we assumed it was, might just be the most exciting thing happening in science right now. If you found this video as mind-bending as I hope you did, make sure you subscribe because we cover the kind of deep, surprising space science that rarely makes mainstream headlines. Hit the notification bell so you never miss a new upload, and if you want more on the question of life in our solar system, check out the video on Europa next, because if you think Mars is surprising, just wait until you see what is hiding beneath that moon's ice. See you there.